Hello, Risky folks. Thank you so much for joining. Rashid here, and today's video is about assembler directives. I feel I should have done this video before, but it's okay. It's not too late. We are still in the course. Okay. So, what are assembler directives? I thought it's I'll tell about these one, and these are part of the reference book that we are covering from Sarah and David. So that whenever these directives you see in an assembly program, you're not shocked to see what is happening there. So directives, as the name suggests, gives direction. So some of these commands which start with these darts, these commands give direction to assembler. Now, assembler's purpose, if you remember, is what? Convert assembly language into machine code. And what is machine code? Just everything zero ones. And that's exactly what we want to store later on in our flash. Okay, so, but all these dart and other these special constructs, these are not converted into machine code. They are just there for the assembler's operation. Understand? So you must be familiar with one of them that we use quite a bit, and that was, remember the label? When we jump to a particular label, again, the label is not converted. Eventually, an address is calculated. A label is just a direction for the assembler. So these are exactly the same, but some of the other ones. I think this is not a complete list, but it gives you some of the common ones and the idea of how they use. The book does give a very good example. So instead of going through this list, what I'm thinking of is just go through this example and explain you that. I think book also gives a good explanation, but let me quickly go through it and you watch my video, and if you have any question, you can ask me. So in this example, first a memory is shown here, okay, where the data is sitting. Okay, so this one, and keep in mind, okay, and I did mention this before, that the memory addresses doesn't mean that all the addresses are actually the memory addresses, right? Remember the concept of memory mapped? Some of the addresses could be that those addresses are for flash, some addresses are for SRAM, some addresses are for some other interrupt controller, some addresses are for a GPIO controller, right? Those memory mapped concepts. Okay, so keep that in mind, but generally, the text, if you remember, dart text means this portion is all a code. It's an instruction for CPU. It's our program memory. And we will keep that in our flash, in the SOC that I'm building. Okay. Then this section, so dart section is kind of tells, okay, what is this section? I mean, you can also do this or something like this, that it says that any code after that until you see a new command in the assembler, a new directive, this is a constant, or this is a read-only data, RO data, read-only data. We are not going to change it. So we cannot allow, so put it in a memory location where you cannot update this or cannot write into that location, right? Makes sense? Then the BSS and data, these are put on the SRAM addresses. Okay. Now, what's the difference between data and BSS? BSS is, I always forget that. These are, BSS stands for block started as symbol. I don't know why that particular name, but basically the concept is in your C language, you always declare some variables which are not initialized to a value, which is good, right? Because they will be given a value during the runtime. And if you already given them some initial value, then what's happening is your binary code gets bigger because now it needs to put 000 for so many things, right? So your executable is smaller, but when we are allocating a memory for them, we need to initialize them with some 00 here. Okay, so this is for that, uninitialized variable in your code, which are later on given some initialization. Data is the SRAM part. Okay, and SRAM, when you turn off the power, it's gone. Everything is gone. And this is what we will keep in our flash. Okay, so let's start from the beginning. So dot global, any of these, this means this main function is a global. Why we need to do that? Because we will write a bootloader program or a startup code. And from there we will call the main. So start, we do some initialization in the beginning, all the stack pointer or what is where, some other things, but and then eventually we will come to the main program, which is the main program that is running on our SoC or CPU. Okay, we will look into all those examples properly during verification, so don't worry. So we'll come to the main. So main needs to be visible in other codes, so that's why that is global. Dot equal, this is equal, so n is 5. So whenever n comes here and you see that n here and here, instead of n, the 5 will be substituted. Good. Under dot data, which is these are the variables we were going to store in SRAM here. So a is a variable, okay, colon. Dot word mean it's word long. A word is how much? The entire word, 32-bit. Okay, and these are the values it has. It has 1, 2, 3, 4, 5, 6, 7 values. Each value, this 5, even though this is 5, but it's keeping entire, this is word. This 42 is 2a, this is hexadecimal. Minus 88 is this, you can see FF's all ones because it's a negative number. 2 is here, then this negative number, and so on. So these 7 words are for A, this A, right? Okay, str1 is a variable, and it's a string, dot string, and it has this value, not these codes, RISC-V. Okay, so these are how many. So in C language, whenever there is a string, it terminates with 0. So you can see that this is where is it? RISC-5 or V, and then this is a terminated string. This indicates the end of the string, but this place is not used, so it's a gray. Understand that? That's clear? Okay, and these code for RISC, I think I covered those, and in the books you can find that too. Then dot align to. What does that mean? Alignment. So whenever you do something like this, tool internally, this is the power of 2. So it means the data will be aligned in a 4-byte boundary. What does that mean? What does the alignment mean? I think I used this alignment before in an instruction which is not aligned, for example, right? So think of this. So you're familiar with that our memory, our data is 1 word long. We can access each byte separately, but typically our address, for example, let's say this is, here is an 8-bit, but think of that, it could be more than 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. 32-bit address, right? I mean, the only one really is made. So at this address, we have 4 bytes. And if you remember that, if we give this address from the CPU, we can really pull entire byte. We don't need to say, okay, 1 or plus 2 plus 3. Okay, and if the next address here is 4, remember? PC plus 4, and then when we give that address, is pull the entire 4 bytes. Now what if data is stored like this? This is not kind of 4-byte boundary aligned, because the next byte starts here. It was written here. Okay, so in order to access this one, what do you have to do? You have to give this address and only keep these bytes. Then you this address, you keep this byte, throw the other one. So it's a waste of resources and more cycles to access it, right? Not good for performance. So when you use dot align to, it ensures that a 4-byte item starts at an address divisible by 4. So and it ensures that if we give something like this, it this one and it's 4 byte, it will start by 0 from here, not from here. So for example, in this one, it says the next one. So it says the whatever next data or word or variable coming, it should be 4 byte boundary line. So this B starts from here. If we didn't have this thing, then B would have started from here. The 2A would be here and then it finished here. And that will be a problem for accessing. Okay, all right, makes sense. Then this variable C and D, it says the 4 spaces, so 1, 2, 3, 4. Okay, and we are continuing with the 4 byte boundary, right? And this one is 1 space and just initialize with 0. Okay, that's good. Now the next one is 4. Okay, this is this byte align 4 is the same thing as saying dot align 2, because this is kind of becomes 4. So it's byte align, 4 byte align. So it's the same way as of saying that one. Okay. Yeah, so then dot text mean this is our main code, instruction code. This is not in the SRAM portion, but you are familiar with it, so I'm not going to go into this. This is pseudo instruction is use load address. It's not one of the base 37 instruction that we studied, but we can convert this into one of those. All right. So then your main code executes and nothing special there, except that some of the pseudo instructions are used here. And then we have section on read only data, and we have string 2 here defined, which is not shown, and dot end. We just finished the assembly code. Okay, makes sense. I think that was super easy, clear. All right, that's it for now, and I'll see you pretty soon.